just came out.
Okay, so this let me formally introduce Ryann Cartor, which is visiting us from Clemson. Ryann is postdoc-ing Clemson right now, which she hung out with Daniello, and before she was doing her PhD with Daniel, exactly, with Dan Smith-On at Hill, and now she will tell us about the C-star cryptosystem and the family of C-star cryptosystems. So.
And so this is work that I mainly did with Daniel Smith-On at the University of Louisville. And so the point of this talk is really to try to come up with a comprehensive study of the strengths and the weaknesses of the C-star modifiers. And so we're going to be focusing on multivariate cryptography. And so this is a type of post-quantum cryptography where the difficulty lies in the hardness of solving a system of nonlinear equations. And so a specific subset of multivariate cryptography are big field schemes. And those are schemes that are going to rely on the fact that if we have some finite field FQ, so just some field with Q elements in it, and then K is a degree and extension of FQ, then K is going to be an FQ algebra. So the way that we use this, the way that we use this to create a scheme is we are going to have some FQ vector space isomorphism, so it's going to map us from the base field to the extension field. And then we're going to choose some function that's going to map us from the extension field to the extension field. So here's just a nice little visual of what this is going to look like. So your input will be a vector of length n. All of the elements will be an element of FQ. You're going to have some map up to your extension field. And then that function f is going to map you from the extension field to the extension field, and then you'll come back down, and so your output will also be a vector of length n. And so C-star was presented at EUROCRYPT 88 by Matsumoto and Imai. And this is the specific big field scheme where we have a very particular function that maps us from the extension field to the extension field. So f is going to be the FQ quadratic function, x to the q to the theta plus 1, where q to the theta plus 1 and q to the n minus 1 are co-prime. The reason why we need those two things to be co-prime is because we want to guarantee that f will have an inverse. So we're up in that extension field, and we just want to guarantee that there's some way to undo that function f. And so notice that I said that it's an FQ quadratic function. So what do I mean by that? Well, if we think about x to the q to the theta, we can see that that is FQ linear. We can see that x is FQ linear. So the product of two FQ linear terms is going to be an FQ quadratic. And then we are also going to hide f by some isomorphisms. So we're going to mix up the input variables and mix up the output variables. And so the public key is going to be given by the composition of those mixing maps, U and T, and then that central map, F. And so this is going to be kind of a visual of what's going on with this. So just like before, we're going to have our input is going to be a vector of length n. Each element is going to be an element of FQ. But now we're going to mix it up with some affine map U. So normally that's just going to be like a matrix. So now I have my input, mixed it up by multiplying it by that U, and then I'm going to map up to the extension field K, and then I'm going to go from the extension field to the extension field using my FQ quadratic function, x to the q to the theta plus 1. Then I'm going to come back down, and then I'm going to multiply everything by usually another matrix. This time it'll be called T. All right, so the public key is going to be the end result. So I'm going to publish what I get when I compose all of that together. But I'm going to keep T, F, and U, so all of those individual parts secret. So I'll give you guys just another second to look at this. The main thing to remember here, though, is that we're going to be using this function. All right, so C-star was broken in 1995 by Ryann using linearization equations. And so since that time, a number of modifiers have been introduced in the hopes of regaining security. So we're going to go through what some of those modifiers are and talk about what they mean. So the first modifier we're going to talk about is the minus modifier, and this one's pretty easy to understand. So what we're going to do is we are just going to literally delete A of the public equations. So let's say that I gave you in public equations. So I said, here they are. These are my public equations. But then, before I'm going to publish them, I'm going to look at, say, maybe the last A of them, and I'm going to delete them. And so then you can only see n minus A of the public equations. And so that's that minus modifier. There's also a projection modifier. And so what the projection modifier does is it fixes the value of d minus n input variables. And so we're going to call that codimension t. So just the difference between d and n, we're just going to call t. So what I mean is you're going to start with some vector of length n, and then you're going to map it to some vector of length d by fixing these last d minus n input variables. You can fix them as 0, you can fix them as 1, whatever your specific map that you want to do, but that is what we call the projection modifier. So again, we're going to have a vector of length n, map it to some vector of length d. We also have a plus modifier. And what this is going to do is it's going to add p fixed random equations to the public key. So if before I had some public key, and I said, all right, these are all of the equations that I found by composing t, f, and u, then what I'm going to do is I'm going to come up with p more equations and just append those on the end. And when I say random, I mean random in the sense that I'm just kind of grabbing them and sticking them on there. But then once I have them published, they stay the same. So they're not like changing every time. So they're fixed random. All right, and our final modifier is this IP, this internal perturbation modifier. And so this one's a little bit more involved than the others, but it's not bad. All right, so first we're going to say that if I have my plain text vector, and then what I'm going to do is I'm going to find some new affine map S, and I'm going to call S evaluated at X, I'm going to call that Z. Awesome. All right, now I'm going to come up with m quadratic equations, where the ith quadratic equation is going to be called q sub I. All right, so I have some affine map, some set of equations. Then my internally perturbed public key is going to be defined by, so I'm going to have my original public key equation evaluated at x, and to that I will add my new quadratic equation evaluated at z. So for each equation, I'm just adding a little bit more. And so the support dimension of IP is going to be denoted as lowercase s. All right, so what we're going to be doing is we want to analyze both the security and the performance of an NDSAPT scheme. So n is going to be the number of variables. So whenever you originally have your input, it's going to be a vector of length n. D is the degree of the extension. S is the support dimension of IP. A, that's how many equations we're going to remove with that minus modifier. P is the number of polynomials we're going to append to the end of that public key. And then T is the co-rank of the projection. All right, so when I say that we are going to analyze both the security and the performance, what I really mean by analyzing the security is we want to look at the resistance against these attacks that have proved to be the most effective against multivariate schemes. So let's take a second and think about what those attacks are. All right, so the first set of attacks are called differential techniques, and they make use of this differential, or this discrete differential. And so the definition is given here. But what the discrete differential does is it's kind of similar to when we think of normal differentiation, in the sense that it will depress the degree of the function that you are applying it to. But notice it's also going to add an additional variable. So if I start out with a quadratic function, and then I apply the discrete differential, I'm going to end up with a bilinear function. So depress the degree, but then add an additional variable. So Paturin's linearization equations, what those did, how those broke C-star, was he was able to find a linear relationship between the plain text and the ciphertext variables. Because remember, the reason why these multivariate schemes are secure is because it's difficult to solve a system of nonlinear equations. Well, you can also model Patrin's original attack as a differential attack. So you can apply this discrete differential, do some algebra, and you're going to find the same relationship that he found. So another way that you can use the discrete differential is you can try to exploit some differential symmetry. So in this type of attack, what's going to happen is a differential adversary is going to try to find these linear maps M and lambda M such that they factor out of the differential in this interesting way. So I want to find this M and this lambda M such that I can factor it out of the differential. The reason why this is helpful for us, if we can find this, and if we're the bad guys, is because if we can find these maps, then we're going to find new linear combinations of the central maps that are linearly independent of the public key. Because notice, here I'm applying these to the inputs, here I have this applied to the output. And so this effectively gets rid of the minus modifier. So in the attack of S-slash, which was the C star minus scheme, it was the specific parameterization that was believed to be secure. This was broken because you can find these additional linear combinations, or these linearly independent functions, and then you can apply Patrin's original attack because you can get rid of the minus modifier. There are also min-rank attacks. What the min-rank attacks look at are the Q ranks of a specific scheme. So we should probably define what a Q rank is. All right, so if we're given a central map, F, we're going to choose a matrix representation, which we'll call capital F, of that function, such that if I apply these x vectors symmetrically to this capital F, I'm going to get my original function. So this capital F is really just a matrix representation of my original central map, lowercase f. So we call capital F the quadratic form. So then the Q rank of F is going to be just what we think of as normal rank of that matrix, capital F. So these are going to be two different examples of what these Q rank matrices might look like. So this is an example of what the quadratic form of an HFE polynomial would look like. So HFE is another multivariate scheme, very similar to C star, but instead of having that x to the q to the theta plus 1 function that we've been talking about, it replaces that central map with just a more general polynomial of degree bound d. So the only non-zeros in that quadratic form are going to be contained in that upper d by d block. This is what our quadratic form of our C star central map is going to look like. So remember, our function is x to the q to the theta plus 1. So the way that I can represent that as a matrix is I'm only going to have non-zero elements in the 0 theta if and the theta 0th coordinates. And so as you can see here, both of those matrices are going to have pretty low rank. And so the main goal of this min-rank attack is we want to find linear combinations of the matrix representation of the public key that have low rank. Because I know that that central map has low rank. So I want to be able to find a linear combination of the public key, so the stuff that I can see that has low rank, because then I can find an equivalent key to the private key. So this attack is very effective against HFE and C star, just as we saw on the previous page. Those are going to be these maps that have very low Q rank. Any questions so far?
I'm just curious about HFE. That's hidden field equations, right?
Yes, hidden field equations.
So what's this hidden field equation referred to exactly?
It's very similar to C star, where you're hiding things behind an isomorphism. So you have like the things that you're mixing up here, and then you map up. And then, so really the main difference between C star and HFE is just going to be what that function looks like at the top. Just more words in the name.
Okay.
Yeah, no, that's a very good question. Yes?
So the attack would have to find the capital F in the middle on the last slide?
It wants to find, so we know that this capital F has low rank. So we want to find a linear combination of the public key that we could then use to find an equivalent key to that capital F.
Okay.
Yeah.
So F's already established at the beginning of
Yes.
the encryption scheme.
Yes.
And then the attacker is just trying to find an F that doesn't necessarily have to be the same, but
Yes. Yeah,
okay.
mostly. Good.
How? I guess how does one find just a generic F that?
Well, so you're really looking for, so if I have some public key, and I'll say it's equal to like P1 all the way to like P sub n. And so this is what's public. What you're gonna try to do is you're gonna try to find some linear combination of, you're gonna make each of these a matrix, and then you're gonna try to find a linear combination of that has low rank. Computers.
Okay, yeah.
Strategy and then computers.
I think I got it.
All right, cool.
Thanks.
You're very welcome. All right, and then our third attack that is the most straightforward are these algebraic attacks, where we're just gonna try to directly break it. And so these are normally established by trying to find Grosvenor bases. So the main use of a Grosvenor basis is to try to solve a system of polynomials. How do you find a Grosvenor basis? You will use an algorithm. And so probably the most common is going to be Fauger's F4. Bookberger was the one to really have the first algorithm, and then there's a lot of research into what's the most efficient algorithm, how can you do that. But what we really care about is the fact that the complexity of solving a system directly is going to rely on the degree of regularity. Now, one way to define this degree of regularity is going to be kind of as this first fall degree, which is the smallest degree at which a non-trivial relation producing a degree fall is generated in the Grosvenor basis algorithm. And so really the takeaway here is, in order to show that it would be difficult to break a scheme directly, is we want to find what the degree of regularity is going to be. All right, so those are the attacks that we're going to try to be secure against, or at least we want to show if we are secure, if there are weaknesses. And again, what we're talking about is this ND-SAPT scheme, wherein I'm going to have an input, and it's going to be a vector of length n. K is going to be a degree D extension of F sub q to the D. S is the support dimension of IP. I'm going to delete A public equations. I'm going to append P plus polynomials at the end of my public key. And then T is just the co-rank of the projection. All right, so let's think back to at the beginning when we had that nice visual of just a regular C-star scheme. Kind of looked like a top hat, right? So we had that U, we mapped up, we had that F, we came back down, and then we have that T. So we're gonna have some of the things that are the same as that original picture. So we still have that K being an extension of FQ. We still have phi being our vector space isomorphism. U is still gonna be that thing that's gonna mix up our input vector. And then our function F is still that FQ quadratic function, x to the q to the theta plus 1, that goes from the extension field to the extension field. But then I just told you a whole bunch of modifiers, and so we need to be able to implement those as well. So this is some of the new stuff that we have to adapt. All right, so LT is going to be my projection modifier. So that's just going to be some map from F sub q to the N to F sub q to the D. And then FC is going to be the map that composes my central map, along with that projection modifier. So it's going to take me, map me up, and then map across, just like before. And then in order to add my IP modifier, I need that S function, which is my affine map, which I will apply X to. And then I'm going to have that set of new quadratic equations. Of course, I need that set of quadratic equations that I'm going to append to the end of the public key. And then instead of having another affine map T and an additional minus modifier, I'm just going to let T be an affine map along with the minus modifier. So it's just going to map us from FQ to the D plus P, because remember we had D plus those new P ones, and then we are just going to chop off A of those equations.
So you want to first apply the minus modifier and then the plus modifier?
We do the minus modifier last.
Okay, because then I'm thinking like, then how are you sure you're not deleting some of the random stuff that you added?
That is one of the things, but you don't just delete from the bottom. I keep kind of saying it like you delete from the bottom, but yeah.
So you you add to the bottom, or you add just random?
You can add randomly. I usually end up talking about it like you're adding to the bottom and you're deleting from the bottom, which wouldn't actually make sense.
Right.
But yeah, you can choose which ones you're going to delete and where you're going to put the new ones, so that you don't just delete all of the ones that you took the time to add. All right, and so again, we have our public key is given by the composition of T, F, and U, where this capital F is where I have my projection modifier along with my central map. And then I'm going to add that IP modifier to each one, and then I will append the plus modifier. So we have a new visual, and it's a little bit more complicated than the first one. But we're going to go through it, and hopefully it'll make it make more sense. So again, I'm going to start with a vector of length n, and that's going to be my input. I'm going to multiply it by u, just to mix it up a little bit. So then that ux is going to go to a few different places. So here, I'm going to project it, so that now I'm at f sub q to the d. I'm going to map up, I'm going to apply x to the q to the theta plus 1, and then I'm going to come back down to f sub q to the d. I'm also going to take this, and I'm going to apply it to S, so I can get like that Z thing that we talked about before when we were introducing the IP modifier. And then I'm going to take this information and plug it in to those new quadratic terms. And so each ith equation is going to add that S of X, the Q of S of X. And then I'm going to take that information here, plug it into my new plus polynomials, and then at the very end, I will delete A of the public equations. And then we can call all of that stuff in the middle capital F. So we can think about what each of those things mean individually, and then we can also just think about that as capital F. Any questions about how the modifiers work together? All right, cool. All right, so this whole time I've been telling you that we're going to analyze this scheme. We finally know how we're going to analyze it. We finally know what the scheme looks like. So let's start analyzing. All right, so we want to look at differential analysis. So are we secure against these differential attacks? All right, so C**'s vulnerability to these differential symmetry attacks are provably removed when we have both a projection and a minus modifier, which is shown in all of these papers. So we have on the differential security of multivariate public key cryptosystems, P-Flash, secure asymmetric signatures on smart cards, and an updated security analysis of P-Flash. So if we have both projection and minus, we know that at this point we don't have any differential symmetry attacks that will be effective. All right, so that tells us that ND 0A 0T is secure. All right, but I'm curious about what happens if I have that IP, so that S, and if I have that P, that plus modifier. So the only way that my scheme with all of my modifiers would be vulnerable to a differential symmetry attack would be if somehow IP and plus would introduce symmetry, right? So it's safe without them. What happens if I add them in? So what I'm really asking is, what is the probability that a random function will have differential symmetry? Now, of course, we're not talking about a random function. We're talking about a very specific function, specifically a quadratic function. but this is helpful just for some heuristics. So again, this is the relation that I'm trying to find. So if I'm a differential adversary, I'm trying to find a linear m and a linear lambda m that I can factor out. All right, so we want to consider the unknown coefficients in m and lambda m. So notice that m is being applied to the input variables. Well, we know that the inputs are going to be vectors of length n. So that square matrix M is going to be an n by n matrix. Lambda m is being applied to the output of the public key. Well, we know that the public key has d minus a, because that's what I deleted, plus p, because that's what I added, equations to it. So my square matrix lambda m will have d minus a plus p squared variables. All right, so that's how many variables I have. And then I'm going to have d minus a plus p times n plus 1, choose 2 equations. Why? Don't worry. We will explain it. All right, so when I have this equation, I can think about it in terms of each equation of my differential of the public key. So I don't have to think about it all at once. I can say, all right, how does this work when I apply it to the first equation of the public key, the second equation of the public key? All right, well, they're going to be d minus a plus p of these p sub i's, right? Because that's how many public equations I have. All right, now when I look at this equality, what I can then do is I can think about these, so these maps as matrices. And so I can think about all of this in matrix multiplication. What I see is that my left-hand side is going to be a symmetric matrix. And so I really only have to check the coordinates in the upper triangular part of the matrix, but I do have to pay attention to the diagonal. So that's going to give me, for each of these, I need to check n plus 1, choose 2 equations. And so that tells us how many variables, how many equations, and then we would set them equal to each other. So this equations, these have solution with this probability. Pretty low. So this should give us some hope that when we have all of our modifiers, we're not going to be introducing some symmetry. All right, but then what happens if I just have the IP and the plus modifier? And I do not have my projection, and I do not have the minus. In inoculating multivariate schemes against differential attacks, it was shown that linear symmetry is removed in that case as well. So what we've really seen is that what we need is we need either minus and projection, or we need both IP and plus. So as long as we have one of those pairs, but we need both of them in those pairs, then we're fine. We don't have to worry about those differential symmetry attacks. All right, so now let's think about min rank. So remember, the way that min rank is effective is because we have a low rank of the central map. And so if we can increase the rank of the central map, this min rank is not going to be very effective. The minus modifier, I will show you that it does generally increase the rank of the core map, but I'm going to explain it on the next slide, so just, it's there, we'll talk about it in a second. The projection modifier does not really increase rank. The plus modifier does not increase rank of the central map. The IP modifier has a support dimension of S, and so what we can do is, under an appropriate change of basis of that quadratic form, all IP inputs can be contained in that upper S by S block, and so it's going to increase the Q rank by at most S. All right, so if I delete A equations, my minus modifier will increase it by 2, and then we have the ceiling of A plus 1 divided by 2. My IP will increase it by at most S. So we can see this bound on the Q rank. All right, now let's take a second and explain to you why that minus modifier acts the way it does. All right, so as shown in the key recovery attack for all parameters of HFE minus, we can represent deleting A public equations as a polynomial, which is being composed with the central map, of degree q to the A. So if I'm deleting one equation, I would have x to the q plus this, or if I'm deleting all A, I can represent it as x to the q to the A plus all of those other things. All right, so if this was my original quadratic form, and I can compose my central map with something that looks like this for each equation removed, what's going to happen is, in order to have my central map, or my quadratic form, represent that f, I'm going to have new non-zero elements down the diagonal. So really, once I delete one equation, I'm going to be adding two non-zero elements to my quadratic form. And so we essentially add two non-zero elements to the quadratic form for every equation that we delete. All right, well that sounds a little bit cleaner than that ceiling function that I showed you moments ago. So clearly there's more to this than just this nice polynomial. So what happens when we delete just one equation? So if I only remove one equation, there's going to be some linear map with nullity 1 that when I compose it with C star, it's still going to have rank 2. And so we can always have this change of basis that I can represent C star with one equation removed with a rank 2. And so really what happens is, if I have a C star map, if I delete 1, my rank stays the same, but then when I delete 2, because it only works for the first one, then it's going to delete it. So then if I delete 3, it stays the same. Delete 4, it steps up. So each time you remove like an odd number, it's not changing it because of that linear map, but then each pair is going to raise the rank, which gives us that 2 times the ceiling function of a plus 1 divided by 2. And so, in summary, when we have that NDSAPT scheme, we're going to have our Q rank bounded by that. All right, so that's our Q rank. What's the complexity of min rank? And so we can use analysis from key recovery attack for all parameters of HFE minus, where given our specific Q rank, what would be the complexity of breaking it? And so this is the value that we get. And then we still have our algebraic attacks. And so remember, I told you that when we have those algebraic attacks, we're going to be looking at trying to solve it with Rogner bases. And so the complexity is going to depend on the degree of regularity. All right, well, fortunately for us, we have a bound on the degree of regularity based on the Q rank. We know what our Q rank bound is. And so that estimate is from degree of regularity for HFE minus. And so this is what we found our Q rank bound to be. So then we can use what was given in that paper to have an estimate on our degree of regularity. And then from the degree of regularity, we have an estimate of the complexity of solving the system via algebraic attacks. All right, I'll put all of those numbers again at the end. But there's still some other things that we want to pay attention to. So not only do we want it to be secure, but we want to make sure that it's actually usable. And so one thing that we want to look at is key size. And so we know that we have D minus A plus P public equations, and then we have n variables. And so remember, each of those public key equations is going to be a quadratic function. And so we're going to have n choose 2 for my quadratic, n for my linear, and then plus 1. And so we're going to have n plus 1 choose 2 plus 1 elements from FQ for every one of our equations. So we have a total of D minus A plus P times n plus 1 choose 2 plus 1. So key size isn't too bad, pretty straightforward. And now we want to talk about the complexity of inversion. So we need to be able to send information, we need to be able to receive information. So what we're going to do is we're going to start with this y value. So what we're going to do then is we're going to find all of those vectors w that map to y. So all of the preimages of y under that map T. All right, so all of those vectors, all of those w terms are going to be of length d plus p. So what we're going to do is we're going to kind of separate it. So I'm going to call the first d elements w1 and the last p elements w2. And the first thing I'm going to do is I'm going to look at w1. So just those first d elements. So what I'm going to do with w1 is I'm going to find all of the ws's that are in the output of FIP. And I'm going to take all of those ws's and add them to w1 to get this set, wc. So the reason is I'm basically getting rid of the IP modifier. Usually we're considering base 2. All right, so now that I have those wc's, I'm going to create a set of u's where for each of those wc's, what I'm going to do is I'm going to do FC inverse. So that's my central map and my projection modifier. So once I find those u's, I'm going to be looking for one in particular, such that FIP of u is going to be ws, so the one that we used, and FP of u, so when I plug it into my plus polynomials, will give me that w2, so those last p. All right, so once I can find that u, I'm going to compute capital U inverse of u, and it will give me my original plaintext x. There's a lot going on here. I'll show you an algorithm of it here. So this is the actual math way of typing it all out. Lots of frills and all of that. But so we want to know, okay, what is the complexity of this? So whenever we have a signature scheme, we are not going to have the projection very large, so T won't be that big, because we want to make sure that all of our outputs do in fact have preimages. And so really the thing that is taking up the most time is inverting our central map, so that FC. So if we use an efficient algorithm to invert FC, it's going to be about n to the omega. And then how many times are we going to have to do that? Well, we need to do it for all of the S's, because it's those WS's, and the T's in order. So that's about the complexity of inverting a signature scheme.
So this is the complexity of the signing algorithm or just of the inversion part?
Just the inversion part. Yeah. And then for the encryption scheme, instead of having basically the same thing, the only thing is we will probably need to test more of them, because when we think about this, we're going to probably need to test more of these W's because they may not have as many preimages. So because that T is significantly larger. All right, another thing that we have to pay attention to, specifically when we have an encryption scheme, is decryption failure rate. So that's going to be the probability that x1, x2, and y exist such that the output of x1 and x2 are both y. So the way that we computed the decryption failure rate was we used a simplifying heuristic and said, all right, let's pretend like it's a random function. And then we used Bernoulli trials. And that was done for eFlash, which is an ND0A0T scheme. So basically what we're saying is when we do not have the plus and we do not have the IP, we showed that the decryption failure rate is about Q to the N minus D minus A.
So, sorry to interrupt all the time. So it's interesting because so by decryption failure rate you mean something that you don't have a unique decryption of. It's your
Yes.
It's not like we, for example, in code base we think about decryption that actually doesn't have.
Yeah, no, this would be one that you, like, I sent you something, and then when you decrypted it, you got something that I did not say. So if I said hello, and then you decrypted it, and you got orange, that would be the decryption failure.
But it doesn't actually fail, it just gives you like a wrong.
Yes, yeah, failure in the sense of our communication didn't work, not failure in the sense that there wasn't one. Yeah, good question. Yeah. And so let's think about what happens when we add the plus modifier and when we add that IP modifier. So the plus modifier, what that does is it just gives you more equations that when you're inverting them, your plain text is going to have to also map to the same thing. And so, like I said, what we're considering a decryption failure is if I tried to send him hello and he then found that I had sent orange, that would be an issue. But if I sent hello and then we have all of the normal things and these extra P equations that hello has to also match, then it's less likely that he's going to decrypt it as orange. And then the IP does not have a significant effect on the decryption failure rate. So when we put all of these together, we're going to say it's about the same rate as eFlash, but now that P is going to make the decryption failure rate smaller. And then here are some actual, experiments of this. And so what we have is we can see that our estimate for these is very similar to what we're actually getting. And so, so that impact is going to be our number of equations. And so we can see that it's Q to the N minus the number of equations. And so here, like, we would get -10 and it's -9.62. So even though we did use a simplifying heuristic to get it, it does seem to be pretty close to actual decryption failure rates. All right, so now what we want to think about is what would these parameter spaces be that would really make C-star the best, the most optimal for signature schemes and for encryption schemes. So let's first talk about signature schemes. Notice that really the reason why we want that plus modifier is so that it reduces the decryption failure rate, but when you are doing a signature, you don't have to worry about that. I'm choosing my particular signature and everything, so you don't have to worry about having two things that map to the same output. So we have our differential symmetry, min-rank, and algebraic complexities that we talked about earlier. We have our public key size, and then we have our signing time. And so to minimize these, specifically the signing time, we would want P to be equal to 0, like I said. We would want S to be equal to 0 because we need to have at least one of these pairs. And then we would want T small, so that would make this small. All right, so what I'm saying is I would want a C-star scheme with a relatively small projection, and I want a minus modifier, but I don't want plus and I don't want IP. That is precisely what P-flash is, which is currently the best known C-star, projected C-star minus scheme. And so it appears that it really is a good parameter space in order for security and for use, performance. All right, now let's see what we can find out about encryption schemes. So this one's, there's a little bit more. So I still have my differential symmetry, min-rank, and algebraic complexities. Here's our public key, our decryption time, and our decryption failure rate. All right, so let's look at a few different strategies that we can take. So let's say that A plus S is really large. Well, that would help us in our securities, right? It would make our min-rank and algebraic securities much larger. But if I make it very large, then it's going to increase my decryption time. And I want to be able to decrypt things quickly. So that's something you have to pay attention to. Also, if I want to have a small public key, so here's my public key size, I would want A to be large, because that's what I'm taking away, and I would want P to be small. But when we look at the decryption failure rate, if A is really large and P is really small, we're going to have a much higher decryption failure rate. So there's a lot more give and take in the encryption scheme area. Any questions? That's what I have.
Yes, so I have at least a couple of questions, but first I'd like to hear if someone else has questions.
I have two questions.
Okay, we do one each, Paolo, okay?
Okay.
And I start because of seniority.
You start.
So I'm curious. First of all, so yes, as far as I'm aware, I'm sure you know that this competition.
Yes.
There is one candidate that I know of that is based on HFE,
Yes.
which is GEMS,
Yes.
and has like pretty big public keys.
Yeah.
It's like signature scheme. And so I wonder what's the big term? I was trying to think about. So is that binomial then plus 1 over 2? That's the determine the public key.
Yes.
Public keys. Because n is.
Yes, because we have these quadratic, each of the equations is quadratic, and so that's where we're getting those.
That's the. I mean, this was because Q isn't Q just 2.
Yes.
So that's not big, and then D minus A plus P. I'm sure that's not the part of the.
Yes. It's
I was trying to remember the parentheses.
yeah, and I'm trying to remember, but I feel like a lot of it is because
You get
it's
like
just so
several
much, and it's
kilobytes.
so much larger than the other ones, like in comparison. But alright, so where does that come from? I think it comes from the n, because you're gonna need n to be relatively large.
Yeah, and then of course you're thinking of binomial. So.
Yeah.
Okay. Paolo?
You have a similar question. So, okay, so the fact is that you choose Q equal to 2, right?
Yes.
For instance, which are the values for the other parameters, like A, S? Okay, the ones in the table.
Well, yeah, but I just realized this is just for the decryption failure rate. But yeah, this is one, and so these are some small ones that we could do with the decryption failure rate. I thought I had another table where I did actually show you some more reasonable
Okay.
variables, and I'm realizing it's not in here.
Okay.
But they're normally going to be larger, but keeping 2 as the key normally.
Okay. So these ones are like parameters for a toy example, something like this.
Like it's going to be more in like the 200-ish, 50-ish, 80-ish.
Okay. Okay, so I have another question. Can I go, Eduardo? Or?
He's like, my turn.
So, do you have attacks that are based on decryption failure events?
That is the question that Shamir asked, and I have not been able to find one yet, but it also has not been what I've been focusing mainly on. So the question is, can I find a way to attack this knowing that it has a pretty high decryption failure rate? At this point, I don't know one, but I feel like there should be. And so I feel like that's going to be a very good question. We have been looking more, some of the min-rank stuff acts a little bit differently in other circumstances than we originally thought it would. So not in this one, but when we're looking at another paper, E-flash paper. So that's kind of what we've been focusing on. But that is a very good question, and I think it would be a very interesting route to take.
Okay, because the fact is that you need to deal with high decryption failure rate values. Okay.
Mm-hmm.
Okay, I see.
Yeah, and that's also, because multivariate in the past has really just been used for signature schemes. It's not really one that has been used for encryption schemes.
Yes, so
very
this
much
was
in
my
front of
question
that.
actually,
Yeah.
is that traditionally, I mean, we do code base, so as I say, like for us, it's kind of the opposite thing where doing encryption is very natural and doing
Yeah.
signatures is.
Yeah.
So what's this difference? Because now you were talking about C star as kind of like a generic approach, and then you can do signatures and encryption with it, and like, why does it work for one and doesn't work for the other? And it's
So-
my personal ignorance.
Yeah, no, it's, so one of the biggest things is if you have a smaller projection, so that projection modifier, that works really well for signature schemes, but it doesn't allow you to send as much for, the other thing is if you have a smaller projection but a really large minus modifier, that's gonna make you a lot more secure. But if you have a huge minus modifier, it's gonna make decryption a lot more difficult. Now, if you're doing a signature scheme, you know what those are, you can just add them back in and you'll be fine. But when you're decrypting and you don't know what those are, whatever you do, it just takes a lot longer.
So it's just that it's less practical to do encryption, but in terms of security, you just can't do the same analysis.
Yeah.
Any other question? Okay. Well, let's thanks Ryan again for getting this out. Crypto Cafe, I'll see you in 2 weeks. All right. We'll announce this as usual.